Today, let's talk about kernel smoothing. This is perhaps the easiest way to fit a smooth curve. Suppose we are given some noisy data, then we can just take the local average of that noisy data to obtain a smooth curve. So let me give you an example. Suppose we are given pair data xi and yi. We have five data points, means y goes from 1 to 5. Then this is our data set looks like. The easiest thing that we can do is just to take the local average of y to obtain a smooth curve. Okay, the first thing that we can do is to add two padding data points to the first and the last. So after we take in the local average, it will give us the same length after the smoothing. Then we can just take the local average, right? The first points, let's call that y1 bar. It's just going to be the average of the first three values, right? Let's just do it like that. It's going to be 1 over 3 y0 plus y1 plus y2, right? That give us 2. And then y2 bar, I'm not going to waste our time. I'm just write out the whole thing. Okay, so here is the result. I just basically take the local average of the three data points nearby and obtain the smooth value for this data. Then I also plot it on the right. The yellow dots are the data value before smoothing. The green curve is after smoothing. So see that after this local averaging, we are reducing the variability of the data. So that is the idea of local smoothing. If we want to write it down as a formula, we can first define a smoothing kernel for it. So here's our smoothing kernel looks like. We have k of x equals to 1/3 if x is in -1, 0, or 1. And then kx will take 0 otherwise. Okay, then we can write out the local smoothing formula using this function k. So here's what we're going to do. Then we will have y bar of x equals to summation over u, then k u minus x yu, right? So that is the equation for local smoothing. Now we can plug in one example and see why this equation works. Let's plug in x equals to 2, for example. Then that equals to summation of u k u minus 2 yu. Then we can just spell the whole thing out, right? And then we can separate it into this part that let's say that u smaller equals than 0. So k u minus 2 yu, and that term is 0. So for the next term, we will have u equals to 1, right? So that means we have k minus 1 y 1. Then we have u equals to 2, and that gives us k 0 times y2, right? Yeah, this is u equals to 2 case. And then we have the u equals to 3 case. We will have k1 and then y of 3 plus when u is greater or equals than 4, we will have k u minus 2 y u, all of that will become 0, right? Okay, so now we see this y bar here is exactly the same as y2 bar, right? For our local averaging. Now we can interpret this local smoothing formula a little bit more. A nice way to think about this function k is that it can be thought of as a detector. So let me just draw a picture here. So this is our function k. And then for this local averaging formula, we're basically just sliding this detector to the right as we move up to different x values, right? So so here the detector, let's say the position is at x equals to 2. So here actually the detector is actually discrete, right? I'm drawing a continuous detector, but you know what I mean. So this is actually a discrete detector that takes the value of 1/3 for these three values and then zero elsewhere. So that means in here we are kind of using this detector K to dot with the data to obtain our smooth value. Then we just perform the sliding window for this detector gradually to the right, where we can, after a few steps, we're gonna have the same detector at a different x position. And this operation is also known as convolution. Let me just clear up the space a little. So this is also called convolution. And we write that as y bar of x equals to k of x star y of x. There's a technical note here is that for the sign of this convolution, I think it's this, right? It's u times k x minus u with yu. Right, but you'll see here that our function k is symmetric, so it doesn't really matter. As we use, for most of our local averaging formula, we're just going to use the symmetric function k. So that means kx equals to k minus x, right? So that is a common way we apply for the local averaging formula. And then you see that this local averaging equation is the same as the convolution performed between k of x. Also, I should emphasize that this k x needs to be a probability density function. So kx need to be a probability. When k is a probability density function, that's when convolution is the same as local averaging for the function y. Okay, so this also means that there's not one unique way to take local average. So let me just give you a few quick examples, right? Okay, so this is the example that we use, right? We use equal weights 1/3 over the three nearby points, but we can also put some weight on it, right? You can use, for example, we can use 1/2 and then 1/4 for the two nearby points, right? So that's also going to work. Also, we can include more points into the neighborhood, right? We can do something like this. Let's say this is 1/3. We can add 5 points to it, right? And then we can say these are 1/4, and these are 1/12, right? As long as it's a probability mass function, we can use that as a smoothing kernel, and then apply the convolution formula to obtain the local average for the function. So that is the main idea. Okay, so now let's think about what happens if we have a continuous kernel and a continuous function. For this current example, I should say emphasize this is a discrete kernel and a discrete function y. And that is the first case. So the second case we're going to look at is it's going to be a continuous kernel and a continuous function y of x. So let's do that. Okay, so here the idea is very equivalent. We just replace the summation with an integral. So we'll have y bar of x equals to k of x. Let me just put a subscript sigma there, and we'll see that in a second. Convolution with y of x. Then we're going to expand it out as integral k sigma of u minus x y of u du, right? So that is the equation. You see it's very similar to the summation, except we replace that with an integral. And this can be used to smooth out a continuous function. Suppose that we have a function like this. Suppose this is y of x. Then we can apply this convolution formula to obtain a smooth curve as y bar of x. Right, so the idea is the same, right? We can interpret it as a local averaging. So let me just say that, let's say that k sigma u of x, suppose this is a density function. So this is a density function. Okay, so the idea here is the same, right? Suppose we are given one particular value of x, then we are taking the average of this function y using the weight coming from this kernel, right? K sigma. So this K sigma here needs to be a probability density function. So K sigma of x is PDF. For example, one common choice that we use is just going to be the Gaussian function, the Gaussian PDF, right? So K sigma of x equals to 1 over square root of 2 pi sigma exponential minus x square over 2 sigma square, right? So that is a common choice we use to do the weighted local averaging of a function. So this sigma parameter here is very important. That is called the bandwidth. Sigma is called the bandwidth. Right, so you can imagine that when sigma is higher, that means we are considering more points into the local average formula, right? So for example, we are basically for each data points, we are sampling, we're kind of taking the local average using a kernel function, right? So that's going to be K sigma we're using at each point, right? Or the sigma here, the sigma parameter here dictates how much, how concentrated we want this to be, right? Depending on that, we can obtain a curve that is either very smooth or a little bit bumpy, like the original data. This means that when sigma is large, and the y bar of x is going to be smoother. Okay, now let's get into the third case. That is more closely related to the real world problems. It's when we use a continuous kernel on discrete data and discrete y. Okay, let me show you that in a second. Okay, so here is the idea. You see, this equation is it's just applying the convolution formula, but replacing the discrete kernel with a continuous kernel. Right, so that is the idea. But you see that the problem in here is that this K sigma here is no longer a probability mass function because it's not normalized. So all we need to add here is to normalize this thing. So we're just going to divide this by the sum of this. Right, so one way you can think about this, a very nice way is just think of this as a weighted average, right? We can treat this kernel function here as a weight w of I. Then the denominator will become the sum of wi, right? So and you see this wi actually depend on the particular position x, right? So uh, it's a kind of a position dependent weight, right? So that can be also written as wi of x times y of xi sum over I over sum of all weight, right? So now this becomes a weighted average formula for all the data points. So for this K sigma here, like we want this just to be a probability density functions. So K sigma can be it's just a PDF, and we can still use the Gaussian PDF. That's a very common choice. So example, so it's still going to be the Gaussian PDF. Okay, so here is a plot I generated using this kernel smoothing formula. And suppose we have a lower sigma, right? Sigma is a bandwidth. Right, so you see that the effect of sigma pretty obviously that if the lower the bandwidth we use, that means we are kind of taking the average using fewer points, right? We are putting very high weights on the few points nearby, right? So that means we'll have the density function sample something like this, right? So each point we're gonna have a very sharp density function as the local average. And then when we use a larger sigma, we're putting more nearby points into the local averaging. So that's when the curve we obtain is smoother with a higher bandwidth. Okay, so that's pretty much about kernel smoothing. So, okay, one more thing here is that this equation here can be easily extended into multi-dimensional case. So that's when our x belongs to Rd, all we need to do is to pick a multi-dimensional. So K sigma is going to be a multivariate PDF. Right, so that's the only thing we need to change. For example, we can use multivariate Gaussian. So that's the only thing we need to change moving from one dimension to multi-dimension. Okay, so in the next video, I'm going to talk about kernel density estimation, which is kind of a special case for this kernel smoothing formula, except that we want to estimate the density of the data points rather than smooth out the signal.